Okay, so now we're going to go back to some of the applications that we saw in the previous sections. We're trying to find the area of the region bounded by the curve. So if we're finding the area of the region of this, remember that is the definite integral. If we want to find the exact area, we estimated it with rectangles. That's not what they're asking. And they want it from the x-axis and the line x equals 3. So where does it touch at the x-axis? It appears to me that it touches at that point 0, 0, so it looks like we're going from 0 to 3 of x over x squared plus 1. Okay. Again, if you did plug in 0 into this, you would have y equals 0 over 0 squared plus 1, which is 0 over 1, which is 0. So that implies that that point is indeed 0, 0. That's what it looked like on the graph, and that is indeed what it is. So we want to find the integral from 0 to 3 of x over x squared plus 1 with respect to x. That's how we'd find the area of the region bounded. So how are we going to do this? Well, this is a U-substitution problem. So let's set up our U-substitution. Let's let u equal the higher power. So this would be the x squared plus 1 part of it. The second step again is take the derivative of both sides. So du dx would be equal to, well, the derivative of x squared plus 1 is 2x. Step 3 is solve for dx. When we solve for dx, we'd have dx equals du over 2x. We have to do our substitutions now. Remember, we're always substituting in for dx, and we're also substituting in for u. So let's rewrite that integral. This is going to be step 4. We're going to rewrite that integral. And so this is going to be the integral from, okay, so now we have some work to do. Remember, if we have limits of integration, we wanted to change the limits of integration. So we had two options. We could either write x equals 0 and x equals 3, or we could just change the limits of integration themselves. So let's go ahead and change those limits of integration, because I think that was a little simpler, and I know that's what they did in the book. So we have the x values of 0 and 3, and we have to plug that into the u values, and u is equal to x squared plus 1. So if I plug in a 0, 0 squared plus 1 is a 1, and a 3 squared is 9 plus 1 would be a 10. So these right here are going to be my new limits of integration. My new limits of integration, again, are going from 1 to 10 because I swapped out my limits in terms of u. Okay, so this is now x over, instead of x squared plus 1, this would be u. And then instead of dx, we'd have du over 2x. Notice that our x's simplify, and we can pull out that 1/2 as a constant multiple. Make sure it's on the bottom. This is from u equals 1 to 10 of 1 over u du. Now we could go ahead and do our integration because everything's in terms of u. So this would be 1/2 times the natural log of the absolute value of u, evaluated from 1 to 10. Again, resist the urge to back substitute for u because we changed our limits of integration here. So now for step 6, we just evaluate it. This would be 1/2 times the natural log of the absolute value of 10, which is just 10, right? Minus the natural log of the absolute value of 1, which is just 1. That's perfectly fine. Well, the natural log of 1 is 0. So what does our final answer look like? I'm getting 1/2 times the natural log of 10. Again, I don't need the absolute values because 10 is a positive number. If you put the absolute values, though, in your final answer, and let's say WebAssign counted it as incorrect, I would give you full credit for that, just to let you know. So that's the exact answer, 1/2 times the natural log of 10. I looked in the book, and the book also estimates it as a decimal. It didn't ask you to estimate it as a decimal, so I'm just going to leave it as the exact answer. Okay? Let's go ahead and move on. Let's look at the next problem right here. It wants us to integrate 3x squared plus 1 all over x cubed plus x. What a nice hint of this is notice that the difference in the x's and the powers of the x's is by 1, okay? And that's because we're thinking about the derivative. For instance, if I take the derivative of x cubed, I get that 3x squared that I'm going to need right there. So here we want to find, we're going to use U-substitution. When you see that difference of power in 1, that's a nice trigger to know that you're going to be using U-substitution. So in this case, we're going to let u equal the higher of the two powers, so this would be the x cubed plus x as opposed to the 3x squared plus 1. Again, step 2 is always take the derivative of both sides, so du dx would be equal to Well, the derivative of x cubed is 3x squared, and the derivative of x is 1. Step 3 is solve for dx. So dx would be equal to du over 3x squared plus 1. Now what do? We substitute back in for dx, and we also substitute in for u. Okay, and we're going to rewrite our integral, so let's do that now. Step 4, let me do that in blue. Step 4 would be equal to the integral of the 3x squared plus 1, stays what it is. Instead of x cubed plus x, I write u. And instead of dx, I'm going to write du over 3x squared plus 1. Notice the 3x squareds plus 1 simplify, and I'm left with the integral of 1 over u du. That's easy enough to integrate. We know that the integral of this is equal to the natural log of the absolute value of u plus c. Plus c. And then the last step is just substituting in for that u. Remind yourself that u is equal to x cubed plus x. So on step 6 here, we would have equals natural log of the absolute value of x cubed plus x plus c. That's our final answer. Go ahead and write that the answer blank. Natural log of the absolute value of x cubed plus x plus c. Let's move on to part B. This is where things start getting really, really cool. Here I see a relationship. I see a secant squared and I see a tangent. Okay. One of my defaults in trigonometry when I teach a trigonometry class is to change things in terms of sines and cosines. And that might work in this case. And it probably would work if you did it hard enough and you thought about it enough, but really I have a nice relationship here. Here I have two functions if I wanted to use U-Substitution. I have secant squared of x and I have tangent of x. And I want to relate the derivative of one to the other. I know that the derivative of tangent is secant squared. So that means I'm going to let u equal tangent of x in this case. Okay? Because when I do that as step 1 and I do step 2, which is take the derivative of both sides, I'd have du dx equals, well, the derivative of tangent is secant squared of x. Step 3, solve for that dx. Solve for that dx, and I'd have dx equals du over secant squared of x. Okay? Now what do? I get to do my back substitutions. Got to remember what you're substituting for. We're always substituting for dx, and we're always substituting for u. So let's rewrite that integral. When I rewrite that integral as step 4, this would be the integral of secant squared of x. Instead of tangent of x, I'm writing u, and instead of du or dx, I'm writing du over secant squared of x. Notice my secant squareds of x simplify, and I'm left with the integral of 1 over u du. Simple enough now that we can actually integrate. What's the integral of 1 over u du? That's equal to the natural log of the absolute value of u plus c. No simplification to do there, so we can jump straight to the answer. Remember, all we're doing here is back substituting for u, and when we back substitute for u, we'd have the natural log of the absolute value of tangent of x plus c. Really cool there.